Hello guys, welcome to H2O, the A to Z of chemistry. I am Dr. Ritu Johar, your educator for this course, the periodic table. Today we will begin with lecture 12 from the course, but make sure you have watched the previous ones before viewing this one. Now, this course, we are discussing now the periodic trends in properties of elements, wherein in the last lecture, we started the discussion on ionization enthalpy. And today in this lecture, we would be discussing the trends for ionization enthalpy in the periodic table. So let us study the variation of ionization enthalpy in the periodic table. First of all, let us see a graph for the ionization enthalpies against the atomic numbers of the elements ranging from 0 to 60. Okay, so we have the ionization enthalpies of the various elements plotted, and what do we see is that the maxima of the peaks being formed by the ionization enthalpies of various elements. So we are seeing some peaks. So these peaks, they are occupied by helium, neon, argon, krypton, xenon. What does this mean? That the peaks of this graph, that means the maximum ionization enthalpy is of the noble gases, right? And what do we see at the minimas? Well, the minima or the least ionization enthalpy, they are being occupied by lithium, sodium, potassium, rubidium and cesium. That means the alkali metals, they are having very low ionization enthalpies, and the noble gases, they are having maximum ionization enthalpies. What does this mean? Well, this means that the noble gases, they have high ionization enthalpy. They do not have a tendency to lose an electron. Why? Because they have closed electron shells, they have very stable electronic configuration, and they are not at all interested to become unstable by losing an electron, right? And this you can correlate with the unreactive nature of the noble gases also. We call them inert gases because they are not chemically very active, right? So that is the reason why they are not chemically active, because they have stable electronic configurations. They do not have a tendency to lose electrons. Okay, so next, what about the alkali metals? The alkali metals, they are having the low ionization enthalpy. That can also be seen from their electronic configuration. All of them have one electron in their outermost shell, and which they want to lose so that they can get the nearest noble gas configuration. And hence they have low ionization enthalpies, and this can also be correlated with their high reactivity. You must have studied in your junior classes that sodium is kept under kerosene or oil because it reacts with air and water very fast, right? And that reaction is explosive. So you have been studying. So now you can get the reason for that. Why sodium is so reactive, why the alkali metals are so reactive, because they have low ionization enthalpies. They lose their electron quickly, and that is responsible for their metallic nature. Okay, so now what do we see? That's the ionization enthalpy 1. So we are talking about the first ionization enthalpy because we are talking about the loss of one electron over here. So this is going to generally increase as we go across a period. So across a period, what we see is that there is increase in nuclear charge. There is decrease in atomic size. The effective nuclear charge hence increases if we have seen the cumulative effect on the ionization enthalpy, and hence it is going to increase. So now let us see what are the exceptions we see in the case of periods. For this, let us see this graph, which is basically the enlarged version of the previous graph. We have the atomic numbers from basically what we are seeing is from lithium to neon, that is the second period elements versus their ionization enthalpy. And what we see, the general trend is basically from lithium to neon, or in the period, the ionization enthalpy values, they increase with increase in effective nuclear charge. But what we see for beryllium is that it has a higher ionization enthalpy than boron, and nitrogen has a higher ionization enthalpy value than oxygen. So let us study why is it so. First of all, for beryllium, being greater than boron is because of the more stable configuration for beryllium, which is 1s2, 2s2. So we have the fully filled S subshells over here, and then boron, it has a partially filled P subshell, right? So therefore beryllium, this has a more stable configuration. Then the 2p electron in case of boron, this is better shielded. So better shielded means that the effective nuclear charge is going to decrease, and hence the electron from boron that can be removed more easily. Similarly, the 2p orbital, this is lesser penetrating than the 2s orbital, and hence it is easy to remove an electron from the 2p orbital as compared to a 2s orbital. So we have therefore the ionization enthalpy in case of beryllium being more than that of boron. Now let us see oxygen and nitrogen. So this you can again understand because of the stable electronic configuration of nitrogen. So nitrogen has 1s2, 2s2, 2p3 as the electronic configuration, which means that the p orbitals, they are partially filled, and this is much more stable than oxygen electronic configuration, where we have the partially filled 2p orbitals. Okay, so now similar on this trend, we will have the third period as well. We will see that the ionization enthalpy of aluminium, this will be less than that of magnesium, and sulfur will be less than that of phosphorus, right? So aluminium less than magnesium is basically same lines as beryllium and boron, and sulfur and phosphorus same lines as oxygen and nitrogen. So I hope if this comes as a question as well, you will be able to write. Next, we can similar see the trends as far as the fourth period are also concerned, where we will have the ionization enthalpy of gallium being less than that of calcium, and then for selenium it is going to be less than that of arsenic. Okay, and remember over here that the fifth and the sixth period, they are going to follow the regular trends. Regular trend means that from rubidium to xenon and cesium to radon, there is going to be an increase in the ionization enthalpy values with increase in the effective nuclear charge, or with increase in the atomic number as we are moving from left to right in the period. There is no irregularity seen like we have seen in this case in the second, third and the fourth period. So next exceptions that we have to understand is for the transition elements. So the transition elements, if you see the values, general effective nuclear charge, that will be increasing with the increase in atomic number, and we see that the ionization enthalpies, though not much a difference between them, they are increasing from the first element to copper. What happens after copper is that we see that there is a sudden increase in ionization enthalpy. The ionization enthalpy value is increasing, but there is an enormous difference between the two values of copper and zinc, and this is again attributed to the fully filled configuration in case of zinc. And similar will be the case for the 4D series from silver to cadmium, and then 5D series from gold to mercury. Okay. Now, let us see what happens in a group. So, if you consider again the same factors for the ionization enthalpy in the group, we see that there is increase in atomic size, increase in nuclear charge, and increase in shielding effect. And what we find is that the atomic size, this is going to overshadow the effect in nuclear charge values, and we see that the atomic size increases and the ionization enthalpy therefore is going to decrease, because the outermost electron, this is farther away from the nucleus, and hence it is easy to remove that. So you can see this graph as well, which is showing the trend from lithium to cesium, that with the increase in atomic number, that is as we are moving from top to down in a group, the values of the ionization enthalpy, they are decreasing. And the ionization enthalpy value and the atomic radius values, well, they are closely related properties. Why they are closely related? Because both of them are dependent on the same two factors, that is the attraction of the electrons towards the nucleus and the repulsion of electrons from each other. So I hope you can understand this very well now. So now let us see the exceptions in the groups also. So the first exception is in the 12th group that we've already discussed, that zinc, cadmium and mercury, they will have high ionization enthalpies compared with the rest of the transition elements because of the stable electronic configurations. Coming up to the 13th group, well, this is again remembering that the ionization enthalpy values down the group, they generally decrease. But what we see is that from boron to aluminium and then gallium, what we see, there is not a decrease, but what we find is that aluminium and gallium, they have almost similar ionization enthalpies. In fact, gallium is slightly more than aluminium, right? And why is it so? Again, because of the introduction of the 3D shell before gallium, and the 3D electrons, they are going to have a poor shielding effect. Similarly, when we see indium and thallium, they almost have the similar values of ionization enthalpy. In fact, thallium having higher values. Why is it so? Because of the incoming of the 4f shell. So 4f electrons, they are again going to have a poor shielding effect. Again, the nuclear charge values, they are going to increase, and hence we have higher ionization enthalpy for thallium also, right? So gallium having higher ionization enthalpy or almost equal to aluminium, and thallium having higher ionization enthalpy than indium. Okay, so next coming up to the 14th group, and for the 14th group again what we see is the difference in the values of tin and lead. So lead is going to have a higher ionization enthalpy than tin, that is again because of the 4f electron poor shielding. Then we can again see the various groups of the transition elements. So the ionization enthalpy of the 3D series, they are going to be almost equal to the ionization enthalpy of the 4D series. But what we see is that for the 5D series, the ionization enthalpies, the values, they increase rather than decreasing. Right? So down the group, they had to decrease, but we see they are increasing, and that is attributed again to the lanthanoid contraction, that is the filling of the 4f electrons, right? The only group that you see the normal trend is the group 3 elements, that is scandium, yttrium and lanthanum. The values, they are decreasing down the group, that is because the 4f electron filling has not yet started as far as the group 3 elements are concerned. So right, I hope you can understand these now very well. So let us see what are the applications of the ionization enthalpy. So the first application is that ionization enthalpy, that is inversely proportional to metallic character. More is going to be the value of ionization enthalpy, lesser is going to be the element's metallic character. Or if less is the ionization enthalpy, more is going to be the metallic character. Why so? Because if low ionization enthalpy, the element can lose electrons easily, and hence it is a characteristic of metals. Similarly, you can understand this as far as the reactivity of metals is also concerned. The metals, they are more reactive when they can lose electrons easily, and that is when the ionization enthalpy values, they are less. Next, we have the reactivity of non-metals. This is proportional to the values of ionization enthalpy. More is going to be the value of ionization enthalpy. This means that more difficult is to lose an electron, and if there is a tendency not to lose electron, that is a characteristic of non-metals, because non-metals, their reactivity is governed by the gain of electrons, right? So the losing tendency is less and the gaining tendency is more as far as non-metals are concerned. Then we can understand the oxidizing capacity also. So the elements, they are good oxidizing agents when they get reduced themselves. Getting reduced means gain of electrons, and gain of electrons means not wanting to lose electrons. Not wanting to lose electrons means they should have high values of ionization enthalpy. So if the element has high values of ionization enthalpy, they are good oxidizing agents. Next, we have the ionization enthalpies being directly proportional to the positive oxidation state of the elements. So again, you can understand this even in the correlation to the atomic radius. So the atomic radius of the parent metal is more as compared to the cations, and Fe+3, you saw the Z by E ratio, that this was Fe+3, that was the maximum. It had the smallest atomic radius. Smallest atomic radius means that the nucleus is attracting the outermost electrons the maximum. So the ionization enthalpy in that case would be more. So we have the ionization enthalpy directly proportional to the positive oxidation state. And similarly, this trend also for oxygen O negative and O2 negative also you can understand in terms of ionization enthalpy as well now. So that would be all for this lecture. I hope you have understood what are the trends we see in the periodic table as far as ionic enthalpy are concerned, and then we also have seen what are the exceptions we see in the general trends, and we would be continuing now further in the periodic properties with the next property, that is electron affinity, in the next lecture. So I hope you will join me back. Till then, if you have any doubt, please feel free to mail us at h2ochemistry@gmail.com or put that in the comment section as well. If you've liked the lecture, one more favor for us, that is going to be just click on the like link below the video and do subscribe to our channel H2O and click on the bell icon to get a notification when we put up the new course for you or a new lecture for you. So stay tuned for the next lecture. Bye. Have a nice day.